लेकिन सॉफ्ट किए हम। ठीक है white board
Class will be starting in 2 minutes. Hello everyone watching this recording. Let's start today's problem solving session, which is based on what is taught in week 6 of NPTEL Analog Communication course. So today the assignment will be based on lectures 25 to 30, that is PLL, phase lock loops and channel. These are the two topics on which today's assignment is based on. So if you want to follow, please complete lectures 25 through 30 corresponding to week 6 of analog communication course, and then you can watch this recording of problem solving sessions. So let's begin with question 1. In question 1, the phase lock loop circuit can be used for which frequency? For frequency and phase tracking. So the statement is phase lock loop circuit can be used for frequency and phase tracking. Is this true or is this false? So we know that phase lock loop, as the name suggests, locks the phase of the target with the locks the phase of a signal with the phase of the target. So it tracks the phase of the target signal. So of course it can track phase. But if you might recall, what is phase? Phase is omega t plus phi. So phase is 2 pi ft plus phi. So phase is proportional to frequency because phi is constant. Phase is proportional to frequency. So if phase is getting tracked, then frequency is also getting tracked. So A, true. PLL tracks both phase and frequency. PLL tracks both phase and frequency. Okay, let's go to the next question. Consider a phase lock loop circuit with following specifications. The input signal is xt equal to sin theta it. Output of the voltage controlled oscillator is yt equal to 2 cos theta naught t. The constant of VCO is c equal to 1 and its free running frequency is omega c. Assume that the transfer function of the loop filter is hs equal to 1 and the phase error theta e equal to theta it minus theta naught t will be small. If the input phase theta it equal to omega c t plus phi naught, then the steady state error is given by. Okay, so the phase lock loop is getting an input signal xt equal to sin theta it, and the output of the VCO is yt equal to 2 cos theta naught t. So the constant of the VCO is 1, so there is no gain in the VCO, and the free running frequency is omega c. So the phase error theta et equal to theta it minus theta ot. So if the input phase is omega ct plus phi naught, then what is the steady state error? That is the limit t tends to infinity of theta et. So this one needs the transfer function analysis. So here we can see that the small phase error of a phase lock loop is basically the second order system. So S by S plus AKHS into omega naught minus omega c by s square plus phi naught by s. Now limit theta e tends to limit t tends to infinity. This is theta es. Sorry. So limit t tends to infinity theta et is equal to limit s tends to 0 s theta e s. So limit s tends to 0 s theta e s. So let's put s tends to 0 here in this and then so this will evaluate to limit s tends to 0 limit s tends to 0 ss square by s plus akhs. Hs is 1, so 8 and 8a are also 1. So hs, a and k are all 1. K is the PLL gain and A is a constant and Hs is the filter gain. All are 1. So s square by s plus 1 into omega naught minus omega c by s square plus phi naught by s is equal to limit s tends to 0 1 by s plus 1 omega naught minus omega c plus phi naught into s. So if you put s equal to 0, you will get omega naught minus omega c. So this is the steady state value, omega naught minus omega c. Now at t tends to infinity, omega naught is equal to omega c. Therefore, this will be equal to 0. So the steady state error of this loop will be 0. So what does this steady state error being 0 mean? The steady state error being 0 means that the PLL at time t equal to infinity, so that is after a very long time, the PLL won't have any error. So it will perfectly track whatever the phase it wanted to track if you allow it to run for t equal to infinity. But practically nothing runs for t equal to infinity, so we get some error. But in the limiting case, this derivation states that in the limiting case, we will in the limiting case we will get 0 as steady state error. Okay, so we get steady state error as 0. That means at t equal to infinity, the PLL will perfectly track the phase of the signal that it wants to track. Okay, for the same PLL circuit described in question 2, assume the input phase to be theta t equal to omega c plus into 1 plus delta t. In this case, the steady state error is given by. So, the input phase is now not the free running frequency, but there is some error. So, we know that in the steady state, in the steady state limit t tends to infinity, theta et, we have found it to be omega naught minus omega c. So they are saying omega naught is omega c into 1 plus delta. Question 3. So we get delta omega c. So the answer will be delta omega c. Correct answer is delta omega c. So we know that the steady state is omega naught minus omega c. So if the input frequency is omega c into 1 plus delta, then the steady state error will be omega c into 1 plus delta minus omega c. Okay. Now again we have the same frequency. Now they are saying omega naught equal to 2 into 10 to the power 6. Omega c is 10 to the power 6. So note that the small can no longer note that the small phase error approximation. Okay. So the thing is, the small phase error approximation applies when omega naught and omega c, the input frequency and the free running frequency of the VCO, are same. So the VCO should be able to generate a signal that is close in frequency and phase to the input signal. If the input signal is wildly different from the oscillator frequency, so the oscillator can simply no longer generate the frequency required. So we cannot have the small phase approximation previously having. So the small phase approximation cannot be applied here. If the initial phase error is pi by 12, then the equilibrium value, okay. So they are saying that the input frequency is 2 into 10 to the power 6. The free running frequency is 10 to the power 6. The VCO constant is 2 into 10 to the power 6. And the small error phase error approximation thus can no longer be applied. So if the initial phase error is theta e naught equal to pi by 12, then find the steady state phase error. Okay, so now the large scale error analysis. So the difference between the input and the phase lock frequency, free running frequency for this phase lock loop is large. So instead of small scale analysis, we will find the large phase analysis. So the large phase analysis, sorry, this will be question 4. We have to do large phase error analysis. Okay, so for large phase error analysis, d theta t dt is equal to omega naught minus omega c minus ak sin theta et. So this is the differential equation. This is not the exact solution, this is the differential equation. Now we have to solve this differential equation to get the result. Now it is given that k is equal to, so it is given a equal to 1 and k is equal to half into c into b, where b is 2 and c is 2 into 10 to the power 6. So k evaluates to 2 into 10 to the power 6 and a is 1. So k equal to 2 into 10 to the power 6, the VCO constant, and a is 1. Sorry about the disconnection. So okay, so a equal to 1. Therefore, the equation becomes d theta et dt. Omega naught is 2 into 10 to the power 6 and omega c is 10 to the power 6. I think omega naught is 2 into 10 to the power 6, omega c is 10 to the power 6. So 2 into 10 to the power 6 minus 1 into 10 to the power 6 minus 2 into 10 to the power 6 into sin theta t is equal to 1 minus sin theta a into 10 to the power 6. Now let's write x equal to sin theta a. Sin, sorry, x equal to sin theta, x equal to just theta et. Therefore, just for brevity, this equation becomes dx dt is equal to 1 minus sin x into, and instead of 10 to the power 6, let's write n. Let's write n equal to 10 to the power 6. So n is a constant. So dx dt equal to m into 1 minus sin x. Now to get equilibrium, dx dt equal to 0. For equilibrium, dx dt equal to 0 implies okay. Sorry, there was a brief mistake. This is 2. So 1 minus 2 sin x. So 1 minus 2 sin x is 0. Or sin x is half. Sin x half means x equal to n pi by 6. Where n equal to 0, 1 up to dot dot dot. So theta et equal to n pi by 6. Now, therefore, since n first pi by 6, theta et equal to pi by 6 is a valid solution as pi by 6 is greater than pi by 12. If this was something else, say pi by 3, this pi by 12 would have been pi by 3, then pi by 6 wouldn't have been greater than pi by 3. So the initial point would have been greater than equilibrium. So pi by 6 would not have been a valid equilibrium point. Instead, we have to go to 3 pi by 6 because pi by 6 and 2 pi by 6, that is pi by 3, are both lesser than or equal to the equilibrium initial point. So the equilibrium point will be 3 pi by 6 or pi by 2 in that case. But here, first equilibrium is here. Sorry, 3 not 4 because n is not a multiple of 3. No, I'm sorry. N is not 0, 1, 2, 3, 4. It is n equal to all natural number which are not factors of 6. So it's actually n equal to 0, 1. Rather, let's express it like this. X is equal to 2n pi plus pi by 6. So 2n pi plus pi by 6. First equilibrium is at, here n will be 0, 1, 2 and so on. So first equilibrium is at theta et equal to pi by 6. So first equilibrium will get pi by 6. The correct answer is pi by 6 or option B. Okay, so next, let's go to the next problem. The next problem is question number 5 for the same circuit. So we are still in the same problem. Assume the VCA constant to be 0.5, then the equilibrium value of the phase error is. So C is now 0.5. So question 6, C is now zero point 0.5 into 10 to the power 6. So K will be half CB. So half into 0.5 into 10 to the power 6 into 2. So it will be 0.5 into 10 to the power 6. So d theta e dt is equal to omega c and omega naught are still same. So they will be 2 to 10 to the power 6 and 10 to the power 6. So overall it will be 10 to 2 minus 1 into 10 to the power 6 omega c minus omega naught. Let's write the formula. So this will be 2 minus 1. So 1 into 10 to the power 6. A is 1. So it will be 0.5. K is 0.5 into 10 to the power 6. Sin theta e t. Now for equilibrium, d theta e t dt will equal to 0. So 10 to the power 6 minus 0.5 into 10 to the power 6 sine. So this is the final equation that is coming for equilibrium. That such a theta will not exist because sin theta t cannot be greater than 1. So theta e t does not exist in equilibrium. So there is no equilibrium steady state error. Thus, equilibrium point does not exist. Question 5 answer will be D. Answer will be, this is question 5. Answer will be D. Six. For the same, assume the transfer function of the loop filter. Now in question number 6, for the same PLL circuit given in question 2, assume the transfer function of the loop filter to be Hs equal to s plus 1 by s square and the input phase to be theta it equal to omega c into 1 plus delta. All other parameters remain unchanged. So calculate the steady state phase error value. So we will go back to okay. For question 6, we need to go back to the small scale error transfer function. So small phase error transfer function is given as small phase error transfer function is given as theta es is equal to s by s plus 1 s by s plus akhs into omega minus omega naught minus omega c by s square plus phi naught by s. here they are saying most things are same except for the amplitude. Just the a transfer function is s plus 1 by s square. So everything else remaining unchanged. This is s by s plus 1 by s square, and omega naught and omega c are omega naught is omega c into 1 plus delta. So this will be s cube by s cube plus s plus 1 delta omega c plus pi naught s by s square. So this will be s by s cube plus s plus 1 by into delta omega c plus pi naught s. Now this is the steady state error transfer function, small scale error transfer function. Now steady state, to find the steady state value we need to find limit. Now limit t tends to infinity theta it equal to limit s tends to 0 s theta ds is equal to limit s tends to 0 s square by s cube plus s plus 1 into delta omega c plus pi naught s. Okay, now let's put the numerator. So this thing, the denominator will go to 0 and this thing will go to delta omega c. So 0 into delta omega c plus 0 divided by 1. So finally this limit evaluates to 0. So the steady state error is 0. For question 6, the steady state error is 0. The steady state error is 0. Now for question 7, consider a nonlinear channel whose output yt is given as yt equal to x squared t, where xt is the input signal. Let xt be DSB-SC tone modulated signal with message bandwidth omega m and center frequency omega c. If the output of the channel yt is demodulated by passing it through a multiplier with with frequency omega c followed by a low pass filter, then the final output will be. So xt is DSB-SC with a message bandwidth omega n and a carrier frequency omega c. Now the output yt is demodulated by passing it through a multiplier with frequency omega c followed by a low pass filter. So we have a yt. Let's now go to question number 7. Okay, let's go to question number 7. As we said that there is a DSB-SC signal with bandwidth omega m and center frequency omega c. So the output of the channel yt, where channel yt is a square law channel, yt equal to x square t, is passing through a multiplier with frequency omega c followed by a low pass filter. So first we will write the expression of the DSB-SC. First we will write the expression of DSB-SC. xt is equal to cos omega ct cos omega nt. This is the expression for DSB-SC that we will be using. Now the output of the channel, so the output of yt, output of the channel is yt. So xt is yt is equal to x square t. Okay, done. Now, if the output of the channel yt is demodulated by passing it through a multiplier of frequency omega c followed by a low pass filter. So we multiply this yt with a cos omega ct. So the final output is z2 equal to yt cos omega ct. So this will be cos cube omega ct cos square omega nt. Now this is passed through an LPF to get the final output. What will be that? So now we need to expand with cos cube and cos square using trigonometric formula. So Zt becomes 1/4 1 cos 3 omega ct plus 3 cos omega ct. And this is half 1 plus cos 2 omega nt. Now if you multiply all these and collect all the terms, you will finally get the only terms that will survive are the ones which will not have omega ct. So we are passing it through a filter with cutoff frequency omega ct. So if we pass this through a cutoff frequency of omega ct, this whole thing will become zero if we pass through a low pass filter of cutoff frequency omega ct. If this is 0, finally the answer will be 0. Because both of them are omega ct and 3 omega ct. So both of them will be 0 if you pass it through LPN with cut off omega c. So the first term will be 0, and if the first term is 0, the second term will be multiplied with 0, so it's 0. So finally the answer will be 0. Now moving to question 8. Consider a channel whose transfer function HF is given as 1 plus cos 2 pi ft, where mod f is less than 1 by 4t. If the channel, if the input given to the channel is xt equal to cos pi t by 4t, then the output of the channel yt. So xt, we have to first take the Fourier transform of xt. The channel xt is given as cos pi t by 4 pi ft by 4 pi capital T. So the Fourier transform will be equal to cos 2 pi. We will first express it in the standard form, 2 pi 1 by 8t into t. So here frequency is f. So f equal to 1 by 8t. So cos 2 pi ft. So what will be xf? Xf will be delta 1 by 2 delta f minus f naught plus f, delta f plus f naught, where f naught is 1 by 8t, and the hf is given as 1 plus cos 2 pi ft. Therefore, yf will be xf into hf. Is equal to half delta f minus f naught plus delta f plus f naught into 21%. So this is why this exists between 1 by 40, not f less than 1 by 40. So f naught by 2. So minus f naught by 2 to f naught by 2. How much? 2 by 1 plus cos 2 pi ft. Now this exists only if f is between f naught by 2 to f minus f naught by 2. But in this range, now hf equal to half at f equal to f naught and f equal to minus f naught, 0 elsewhere. So in this particular range, hf will be 0. So yf finally will be 0. Question 9. Consider the channel whose transfer function is given as 1 plus cos 2 pi ft e to the power minus 2 pi jf tau. the input is given as same. So this will just this is an exponential. So exponential minus 2 pi j f tau. So this will just get phase shifted by tau. So sorry, this is phase shifted by 2 pi j f tau in frequency domain. So in time domain, it will just get phase shifted by tau. So if your correct answer was option A in question number 8, then in our question number 9, it will also be option A because they will be identical, only they will be shifted by tau. Now going to question 10. Here it is e to the power minus 2 pi j sine 2 pi f t. Here in question number 10, the HF is given as minus 2 pi j sine 2 pi f t. Now xf is given as half delta f minus f naught plus delta f plus f naught, where f naught equal to 1 by 80. Now yf is hf into xf, so this will be exponential this will be half exponential minus 2 pi j sine 2 pi f naught t minus 2, this will be one term, and another term will be plus e to the power minus 2 pi j sine negative 2 pi f naught t. So this will be half exponential minus 2 pi j sine 2 pi f naught is 1 by 80. So putting that, we get sine pi by 4. And here we will have a plus exponential plus 2 pi j, because this negative sign will come out, so it will be plus 2 pi j. So this will be half cos 2 pi j by root 2, something like that. So cos, here you can see the answer. So it will be something like cos pi by 40 t minus 4 root 2. This solution will be uploaded, so please check the detailed calculation. Okay, with this I will be ending today's class. See you tomorrow. See you in the next week.